Hi, I'm Curtis Skinner. I've been with Hy-Pro Filtration about 9 years now. I'm a regional sales manager and have a little over 25 years of experience in the fluid power industry.
Hello there. My name is Richard Trent. I'm a regional sales manager for Hy-Pro Filtration. Been with Hy-Pro for a little over 16 years. Prior to that, about 20 years in the fluid power industry.
Hi, my name is Scott Howard. I've been at Hy-Pro this is my 18th year. I'm a strategic account manager, and this is the Hy-Pro podcast. So let's talk about water. Water is a contaminant that we deal with a lot, and sometimes we hear objections or frequently asked questions from people. I'll throw a couple out at you. There is no water in my oil. If you hear that from somebody, how do you address that?
Well, on planet Earth, there's going to be water in all fluids. There is no way to avoid at least some amount of dissolved water in any lubricant that I've ever encountered. If you're doing tests like crackle tests are only going to pick up water when it's at saturation. But if you're doing a test like a titration of Carl Fisher, where you're actually measuring water as a percent of weight, you will always find some water present. I've never seen zero water on the sample analysis.
Okay, so what if...
Well, I was just going to throw in that the other thing about that is a lot of people, the way they're determining if they have water or not is visual analysis, which one of the ASTM specs is a visual analysis on your turbine oil as one of the primary tests. So one thing to point out is just because it doesn't look milky, that just means you don't have an excess amount of free water. That's not dealing with emulsified, and that's not dealing with dissolved water. And you kind of have to move the conversation there just to see, like he was talking about which test procedure they're using, but it's also a matter of starting to frame that conversation into just because it's not readily apparent doesn't mean it's not there.
Just because you can't see it doesn't mean it's not there.
Literally because you can't see it.
All right, so on that note, we hear this often. People say, well, I don't care about dissolved water. Should we care about dissolved water?
Well, so it depends on what you're looking at. Right? So are you likely to wipe a bearing with dissolved water? No. But are you going to cause metal to start deteriorating, have rust start showing up in bearings and causing problems? Yeah. But you're also moving the conversation from talking about equipment to the life of the oil. So the presence of water is going to accelerate degradation of that oil. And nowadays, especially with the environmental costs and the impact of disposal and people being really conscious of that, talking about what the presence of even dissolved water can do, how the impact it can have on the life of the oil, it's a pretty good conversation to start having. It can be very, very expensive if they don't understand it.
Several years ago, I saw a study by Timken, and Timken said in this study that to achieve 100% of L10 bearing life, if you're lubricating that bearing with a mineral lubricant, which would be like a group 1, 2, or 3, your water content has to be at or below 100 parts per million. In discussing water, all lubricants have a saturation point. At some point in time, dissolved water will become free, and that saturation point is temperature dependent. So you could have a situation where you have dissolved water at operating temperature, and you do the ASTM test that Curtis mentioned a moment ago. You fill a sample bottle up at operating temperature, the fluid is bright and clear, no evidence of water there, but then let's say that sample is allowed to cool down to room temperature, and it could turn hazy because you could have just exceeded the saturation point. The point that Curtis made a while ago, that we may not wipe a bearing at operating temperature, but if that system ever shuts down and then water comes out of solution and becomes free, then you could have the corrosion that he mentioned.
Absolutely. And while we're talking about that, dissolved water also does have an effect on additives.
Most definitely. One of the things that water is going to do to a lubricant, it's a contaminant. It's not supposed to be there. It is there. Any contaminant is going to accelerate the oxidation rate of the fluid. That's going to consume more of the antioxidant packages, just like Curtis mentioned a while ago. As that goes on, lubricant life is negatively impacted.
Yep. And to reiterate, Carl Fisher is one of the best ways, the most accurate ways to determine your water content, which will take dissolved water into consideration, but it is a lab test. So
correct. It's not unfortunately, today there is no way to truly measure in real time the total amount. You can measure water as a percent of humidity within the fluid, which 100% humidity is saturation. You now have free water, but there's not a device other than a Carl Fisher, to my knowledge, that can tell you how much free water exists.
Right.
Oh, it comes down to understanding that, like Richard said, water is a contaminant in oil. And the reason it's a contaminant, one, it's not supposed to be there, but two, it causes damage. It's going to damage the oil, it's going to damage the equipment. Now, how much it's going to damage and how quickly it's going to damage is going to have to do with the amount that's there, but it's still having a negative effect. And removing water is a very cost-effective way to save big money in the long run. When you're having to get rid of oil 5 or 10 years sooner than you would if you had kept it dry, and you're having to deal with the disposal cost, even if it didn't necessarily affect the life of the equipment itself, that's a major expense. There's downtime, there's labor, there's disposal costs. And the goal when you're managing your fluids is to minimize all the costs, to improve all of your efficiencies. So I think it's a matter of a lot of times people just don't think about, they're only thinking about the equipment, or they're only thinking about gross water and major events, and understanding that destroying things over time can have a big effect too. It's not just that catastrophic failure from a whole bunch of free water. Things can deteriorate slowly, but they're still deteriorating, and it doesn't have to happen.
So now let's talk about water removal methods. One of them, let's talk about the positives and negatives of each. Let's start off with the water absorbing filter elements. What are the advantages? What are the disadvantages of using that method?
A lot of times it's more cost effective. It's absorbing water with a filter element is the most expensive way to remove water from a system. But in some situations, a company has offline filtration on a system, or if a user has a filter cart, small system, small amount of water, it may be more cost effective to consume some water absorbing filter media to remove the water than it would be to go to bring in something like a vacuum dehydrator or another piece of equipment. If you're going to remove water that way, since saturation or the amount of water that a lubricant can dissolve is temperature dependent, it's always a best practice to try to do this with the system as low as fluid temperature as low as possible, so that you have more free water, because water absorbing media can only remove free water.
Water absorbing media is an option. There are multiple technologies that you use and you apply depending on the situation. To what Richard said, a single event, an isolated event, some gross free water that you can get out quickly, it's an excellent option. And it's good for people to keep some water absorbing elements if they have filter carts or something on hand. But if you have a more constant rate of ingression, if you really want to get into life extension, they're not going to get you there. But they have a place, and they are a quick. It's interesting because they're the most expensive way, but they can also be the least expensive way. If it's a small event,
right,
it's the least expensive way to deal with that event. It's going to be the most expensive way per the amount of water you're removing. But if you have a small event, it's a fantastic option, and it's good to have that available. It's also good to know that it only gets you so far and only does so much.
That's right. So to reiterate, that does not affect dissolved water content. We would prefer that the oil would be a little bit cooler than hotter, so they have more of an effect. The filter elements do expire, so that could be a potential high cost option, which is, it's not as big of an issue when you have a small reservoir. But what about whenever somebody says, well, I'll just put a water absorbing element on my filter cart just in case? What do you say to that?
It's common practice. If you don't have water, you're not going to consume the water absorbing media itself, so you should get effectively almost equal life on a particulate standpoint, because all of the water absorbing elements that we make also has particulate filtration downstream of the water absorbing media, so you're still getting your particulate filtration efficiencies.
Any limitations on oils, like an anti-wear and extreme pressure, just a rust and oxidation?
Not that I know of.
No, as long as you have seal compatibility, there are some water absorbing medias out there that are not compatible with some fluids. But the type media that Hy-Pro uses is a pharmaceutical grade, and I've never found a fluid to which it's not compatible.
So every once in a while you hear somebody say, well, I have a centrifuge, I really don't need to use a dehydrator. Let's just center on the centrifuge right now. Is this something that's still used often? I don't see it much. It seems to be more of an old style. What's your thoughts?
It is an older technology. There are some customers today that have actually purchased new centrifuges. They're still manufactured today. They are fairly efficient at removing large, gross amounts of water. A place that I see centrifuge used a good bit is in the oil reclamation industry, especially like at tire manufacturing plants, where tire presses leak hydraulic fluid into the pit. This fluid is typically pumped outside, and these companies typically pay another oil service company to come in and process that fluid, essentially remove the water from that fluid, filter that fluid so that it is clean and dry. And the first stage of removing that water is typically through a centrifuge.
The biggest things that I see with centrifuge is they are a very precise piece of equipment that requires very diligent maintenance. In most industrial environments, it's not a good choice, even if it can effectively do the job that they're purchasing it for. The biggest problem you see is they're hard to maintain. So if they're removing a lot of particulate, they have to be worked on. I've seen places where they have to tear them down every shift. So when you're looking at different technologies for an application, one of the things you always want to consider is, what are we going to have to do to keep this thing running? Because we're buying a piece of equipment to fix a problem. Are we adding another problem? The way I look at it, if you're on an aircraft carrier, on a nuclear aircraft carrier, and you've got a guy that all he does is take care of the centrifuge, it'll probably work fine. And it'll do a good job. In an industrial environment where resources are limited and people are pulling multiple duty and people are stretched, I don't see it as an effective tool anymore. 40 years ago, it was the only technology you had, and it does an adequate job. But in the considerations of efficiency, of manpower and resources, I don't think it is anymore. As a general rule, when I walk into a plant that has a centrifuge, it's not running. It's sitting over in the corner disassembled, and people are frustrated with the amount of maintenance that it takes. When you have a high-speed, high-precision piece of equipment that is getting coated with dirt as part of its process, which can affect the balance, the work that goes into keeping that thing running can be very, very daunting. So I think it's a technology that can remove quite a bit. And in a lab setting, or there are settings where I think it's effective. I just think that there are other technologies that have come along that are much more user-friendly and much more practical.
And the biggest drawback about using a centrifuge is it can only affect free water. And in order to affect free water, the lubricant is going to have good demulsibility or have the ability to separate from the lubricant itself. And even in a perfect world, I don't see a centrifuge removing 100% of the free water on a single pass. The best you're going to get would be somewhere in the 90 to 95% range. And since most of these lubricants are lubricating bearings, if your sole method of removing water is with a centrifuge, you are agreeing to always have some water present going through your system.
Yep. I've seen that there's limitations around 1,000 ppm, below which it's not that effective. And also particles below 10 micron in size, the centrifuge really doesn't have an effect. So if a company wants to rely on the centrifuge to really polish the oil, there is some limitations. But I will say from personal experience, I think the biggest negative is the maintenance. It's maintenance intensive, big time. So now let's switch gears and talk about a Coalesce system, and we'll dovetail into a dehydrator. What are the advantages of a Coalesce system, and then what are the disadvantages, including the limitations on the oils that can be used for coalescing?
I think the biggest advantage to Coalescer is the ability to remove massive amounts of free water very, very quickly.
Yep.
And mechanically, they're fairly simple. So as far as moving parts, you have electric motor and a pump, and then you have some valves that need to open and close. So advantages, gross free water, very, very rapid removal.
As well as particulate filtration.
Yeah, but as far as disadvantages, well, they only remove free water.
Only remove free water, that's right.
They only remove free water. They can only be applied to lightly additized lubricants, turbine oils, compressor lubricants, or those R&O lubricants as we call them. But they're also, coalescence is also viscosity limited. To get the full single pass efficiency of coalescence, your viscosity needs to be at or below 32 centistokes, 150 Saybolt seconds, and it works pretty well in the terminal industry. We're using mostly 32 and 46 R&Os, but in some of your heavier fluids that operate at lower temperatures, the viscosity of those fluids are so high that you lose efficiency. In a perfect world, or in say like diesel fuel, that's really a low viscous fluid, it can remove 99% of free water on a single pass. But as the viscosity increases, water removal efficiency decreases, and like both of you mentioned earlier, we're only affecting free water.
Well, and one other thing that we've really started to see the last few years, even if everything's perfect, you've got an ISO 32, R&O turbine oil, temperature's good, everything's good. If that oil's deteriorated, if it's been, if there's oxidation going on, a small amount of oxidation byproducts can negatively affect the ability for the coalescer to remove water. So I think talking about demulsibility is probably a little more in depth than we want to have in this conversation, but that oil needs to be in good shape. It needs to be in good condition. So it is limited in that the oil, it doesn't necessarily have to be pristine, but the oil has to be in fairly new condition for it to work. Now diesel fuel doesn't matter, but as far as lubricating oils, if you start losing demulsibility, the system's not going to work.
Well, I mean, water as a chemical compound is polar. Lubricants, as a rule, are nonpolar, so you can't mix a polar and a nonpolar compound into a true solution. But with the presence of contamination within your lubricant, it could be oxidation byproducts, like you mentioned. It could be an accidental cross-contamination with a lubricant that has detergents or some anti-wear type additives or extreme pressure additives.
An assembly lube. If they did somebody rebuild a pump and used assembly lube.
Any contaminant that has polar compounds is going to affect the fluid's ability to shed water as a polar compound, because polar compounds will try to stick together.
Yeah, the one thing to think about when you're looking at, or one of the things to look at with coalescing, is it's a mechanical separation. So it's dependent on the properties of oil and water being different.
Correct.
If you don't have if you don't have some, or I guess I say, if you have something that is going to cause that to be compromised, it's not going to work.
Yep. So AW, anti-wear additive package, very aggressive. I can't coalesce water out of that type of oil. Extreme pressure, EP additive, very aggressive. It's going to adhere itself to the coalesced media. So we know there's some limitations there. The advantage compared to water absorbing is it continues to shed. So that's
Correct.
good. So the cost, once you purchase it, it's very low. But there is another limitation. Because it's only free water, what do we recommend for our customers as far as the temperature at which they need to coalesce? Higher, lower? What's your thoughts on that?
Well, typically we need to coalesce at a fluid temperature where the viscosity is at least no greater than 32 centistokes, which happens to be where most the lubricant used most often in turbines and compressors. But since those systems tend to run at elevated temperatures during operation of the system, you are raising the saturation point of the fluid, so you're allowing the fluid to operate at a higher water content with the dissolved water that's remaining.
So that's a limitation then.
That is a limitation, because again, we're only affecting free water.
So if I have a limitation as far as being able to use my Coalesce option that I'm considering because of the operating temperature of the oil, it leads us into the vacuum dehydrator. What are the advantages of a vacuum dehydrator, and what's your thoughts as far as where those can be used?
Well, the theory of vacuum dehydration is to vaporize the water, turn it into water vapor, and then the flowing of the air under vacuum through the vacuum chamber removes those vapors out of the system. There, the lubricant falls to the bottom of the chamber, and then it's pumped and filtered back to the reservoir. Water will vaporize, or it boils, at 212 degrees Fahrenheit, 100 C at sea level, as a rule. But when you put water under a vacuum, it will vaporize or boil at a much lower temperature. So all a vacuum dehydrator is doing is playing with that physical property of water. So at a vacuum of around 25 inches of mercury, water will vaporize at approximately 133, 134 degrees Fahrenheit. At that temperature, we're not causing the lubricant to oxidize at any accelerated rate, because most lubricants maintain oxidative stability up to 150 to 168 degrees Fahrenheit. Heat typically is needed to get the lubricant to that temperature before it's exposed to the vacuum. Now, you don't have to have heat for a vacuum dehydrator to remove water, because one of the physical properties of air is that when air is compressed, water will fall out of that air. Because the humidity increases, we've got more water in a smaller area, water falls out. Just the opposite happens when you put water under a vacuum. Not water under a vacuum, but air under a vacuum. When air is under a vacuum, the humidity of the air decreases. So the air flowing into the vacuum chamber has lower humidity than the lubricant has. Humidity is always going to try to equalize in an environment. And with that lower humidity air flowing through the vacuum chamber in contact with the wet lubricant, mass transfer is the term that some people use. But by mass transfer, you're going to be removing water even before you get to that heat. But if you want to remove the maximum amount of water that you can remove and not harm your fluid, understanding that water in that fluid is harming the fluid and it's harming the systems that the fluid is trying to lubricate and protect, vaporizing that water and getting it out removes the water at a faster rate.
And that's important, faster rate, because I think it's real important to mention that if you have to recover a system that has a water ingression, heaters are required.
I would agree.
Well,
Absolutely.
Let's make a point about mass transfer that needs to be understood too. Mass transfer has its place, and mass transfer can be used effectively. But a vacuum dehydrator is a very expensive way to mass transfer. To get the effect that Richard was talking about, the low humidity, you can do two things. You can pull it under a vacuum, which spreads everything out, makes it less dense, or you can just have really dry air. So when you're looking at, okay, I just need a maintenance item, I'm not removing a lot of water, having a vacuum pump and all these mechanical components that are necessary for vacuum dehydration is not an efficient way to do mass transfer. There's another way to do mass transfer, which
Right.
kind of...
Yep.
Mass transfer in a vacuum dehydrator, as you said, is expensive. It removes maybe cups of water a day. Vacuum dehydration, where you're literally flashing the water off as a vapor, because we have heat, we can remove gallons of water per hour. So if you've got a large system and a large amount of water, heat is really needed to get ahead of the water ingression, to actually get the water content somewhere well below saturation. Mass transfer will remove some water, but it's going to remove a very small amount of water over a long period of time.
And if you have an upset condition, mass transfer is going to take an extremely long amount of time.
Days,
to
weeks,
recover.
or months.
Yep. But where the mass transfer is really effective, let's pick on gearboxes and let's say a hydraulic system that uses a fire-resistant fluid. We're not really in a recovery mode. Is it cost effective to use a dehydrator on a gearbox or let's say an EHC system? Or could a mass transfer like a total moisture removal device work?
In those systems, what mass transfer does in those systems, one, having the extremely dry air in the headspace eliminates ingression. These fire resistance fluids are typically hygroscopic. I have trouble saying that word usually. But that simply means that they love moisture. They will pull moisture out of the atmosphere and take it into the fluid. So by having that extremely dry headspace, you decrease the amount of water that's available for the fluid. And then at the same time, because of mass transfer and humidity equalizing, that air then absorbs the water out of the fluid.
So it's nice to understand that different technologies are going to work for different applications.
Yep.
But if you're going to apply mass transfer, there's no reason to spend the money that you would spend on a vacuum dehydrator. And there's no reason to have something that's mechanical that has to be maintained. When you can achieve a low humidity in a headspace and remove moisture without mechanical parts, without a moving piece of equipment to maintain, it's a more cost effective, and it goes back to, once again, people have limited resources. So why not put something in, why not use a mass transfer device that you just hook up to air, and you set it and let it run. Vacuum dehydration is generally the way to go on bigger systems, hydraulic systems, lube systems, that kind of thing. But there is no reason to overcomplicate a problem. If you can fix something simply and cost effectively, you should always go that way.
Yeah,
And that's why we have all these options. That's
typically
why,
you're going to see a dehydrator applied to a system that has constant water ingression.
Yep.
And water is an issue. A steam turbine that has a leaking steam seal, for example, a lube system in a rolling mill where you've got a lot of water spraying in the process, and that water can hit the gearboxes and the labyrinth seals and find its way into the lube oil reservoir. That's a constant issue to deal with. Vacuum dehydration can remove that water if it's sized properly and it has enough heat. We can remove the water at a rate faster than it's ingressed and therefore maintain the reservoir at a water level below saturation. But if you have a system where we don't have constant water ingression, like the fire-resistant fluids whose water ingression is mostly from the environment, gearboxes, in those situations, mass transfer is a much more cost-effective solution as long as you don't have large amounts of water ingressing. A gearbox with a leaking shell and tube cooler, mass transfer is not going to be the answer. That would be repair the cooler, use a dehydrator on a temporary basis to get the water out of there, then you move on. But a gearbox that's getting moisture because there's a lot of steam in the environment, a TMR can eliminate that.
and that's why we offer all these different options. And so we can be called in to help size correctly if it's a dehydrator, or help decide which method is most appropriate for your application, instead of just saying everything is a dehydrator. And in most cases, the dehydrator will be the best option. But there are some applications, like we talked about, where the headspace dryer, mass transfer, is appropriate. In some cases, water absorbing media is appropriate, and in a lot of cases, Coalesce is okay, and it's going to work very well.
Right.
So to sum it up, you do have water in your oil. You do need to test it. And we have the solutions.
We do. It's one of the great things of being an employee of Hy-Pro is that we have multiple solutions for water removal. So we're not pushing vacuum dehydrators because that's all we make. We're not pushing coalescence because, well, that's all we sell. We're not pushing mass transfer because that's all we sell. And we're not pushing water absorption because that's all we sell. We manufacture all four of those technologies, plus some others we didn't touch on to deal with excluding water through breathers such as the trap and some desiccants. But because we look at every possible solution for water removal, excluding centrifuges, we're not in the centrifuge business, but we have all of the technologies. We look at each application, help the customer determine what is the best and most cost-effective solution for their specific issue, and having all of that available is wonderful.
And just to summarize, the reason why we're talking about water is it's one of the top 2 as far as contaminants causing damage. So there you go.
This has been the Hy-Pro Podcast. For more information on any of our products or services, you can find us on the web at www.hyprofiltration.com. Remember, please lubricate responsibly.